All right, welcome back. In this video, we're going to continue our discussion of intervals. In the last couple of videos, we've talked about confidence intervals, but in this video, we're going to introduce a couple of others that are used for different purposes. In fact, we'll talk about the prediction interval and a tolerance interval, and then even a confidence interval for variance. And we'll kind of go through kind of how those are created and how those are set up. You'll see that it's very familiar to what we've done. It's just the formula is slightly different. So we'll work through those. So without further ado, we'll get going. All right, so we're going to pick off the first one, which is our what we call as a prediction interval. So before we've been dealing with confidence intervals, which was always about finding, a range of values that would host, usually it was the population mean or population proportion or some sort of predictive statistic off of the population data, kind of a collective value. But you'll see that in some cases, sometimes we want to do things a little bit differently, and we'll do our best to kind of hopefully clarify the differences as we move along. But the first one up is the prediction interval. We'll abbreviate it as a PI, but basically we're going to assume that we have a small sample from a normal distribution and that we have found the sample mean x bar and a sample standard deviation s. So we've talked about the implications of the small sample distributions, or the student t. Okay, and we use these t statistics to do those. And if you need to review those, head back to our last video where we talk about the student t distribution. It's a very important distribution for cases when the central limit theorem isn't applicable. All right, so we're dealing with small samples, meaning the sample size is less than 30. And then we have the known data from the samples that we're measuring, okay? So what we want to do is a prediction interval where before we were trying to find the mean of all of the data, for the population. Now suppose we want to estimate the value of the next single data point. Okay, so we've done this collection, and then, for the next test, what can we expect to happen? Okay, and it's kind of a confidence interval with those regards, okay? And so again, very similar to what we did before, we're going to use this t statistic on this because the t statistic is for the small samples, okay? And so we're going to do this remapping that we did, like the z standard and the standard normal distributions, and then like we did with the t statistic in the last video, we're going to use x bar minus xn plus 1. So where this used to be the population mean on it, it is now the specific value of the next data point. Okay, that's what this xn plus 1 is, because we're assuming that x is part of a set of x1, x2, all the way out to xn. Okay, but now this is the next guy that would go into that set. So you're doing all your calculations based off of what's happening here. Okay, and then we have our sample standard deviation, and then this correction factor of 1 plus 1 over n. Now your book goes through the derivation of this. I'll leave that as an exercise for you to look at, but for now you can see that the formula is a little bit different, but it isn't any major issue, hopefully. Okay, so, all right, so now this t statistic has a t distribution. Again, we talked about that in the last video, with nu equal to n minus 1 degrees of freedom. Okay, so a 100 times 1 minus alpha % prediction interval for the next data point will be given by this equation. And you see that looks very familiar. Okay, we've got our x bar, which is our estimator, plus or minus or t alpha over 2. Okay, so this is a double-sided distribution that we're looking at. Okay, and then the degrees of freedom n minus 1, or that's what was our new value. All that multiplied by s, all that multiplied by 1 plus 1 over n, all that under the square root. Okay, so that's all there is to a prediction interval. It's pretty much the same process, it's a different band. And we'll talk a little bit about what all this means and its significance here in a second. All right, we got one other interval that we want to do real quick. Okay, that's kind of along the same lines of this, and this is the tolerance interval. Okay, so instead of specifying an interval that just captures the mean, now we're looking for an interval that captures a certain percentage of all possible values. Okay, so say I want to capture 90% of all data values. Now what would the interval have to be? And so this is what we call as a tolerance interval. Okay, now the thing that makes a tolerance interval unique is that there are actually two percentages. Okay, there is the tolerance critical percentage, okay, and then there's the actual degree of confidence to which I'm capturing all of those data points. All right, so you'll see that those will show up, and I'll explain those here in a second. All right, a tolerance interval capturing k% of all values at a 100 times 1 minus alpha % confidence level has the form x bar plus or minus my statistic, or in this case, the tolerance critical value times S, all right? Now, a lot of these values are tabulated for specific K values and for specific confidence levels. Those are tabulated in 8.6, all right? So we're gonna do x bar plus or minus that statistic multiplied by the sample standard deviation. All right, so here I've pulled out the table for you to kind of look at. It's pretty self-explanatory, but the way I wanted to set it up, you'll notice that, okay, over on this side is the percentage of the population that we're capturing coming across the top. The sample size is N, so again, this isn't new, this is N. This one's different than some of the others that we've done where we've been looking for the degrees of freedom. So if we have 20 samples here, we're going to use the 20, not the N-1 value. Okay, this will correct itself for our tolerance cases. So it's a little bit different than the prediction interval in that regards. Okay, the table is split into two pieces. I have a one-sided distribution, okay, and then I also have a two-sided distribution. Most of the time we're dealing with the two-side, but not always, and we've explained the difference between the two of them in the last video. Okay, once you've chosen whether it's a two-sided or a one-sided, then we go and we look at the confidence level that we want. So this table is only tallied for 95% confidence and 99% confidence. Now you can find other tables and other resources that will have more than this, but for our textbook we're just focusing on these. The tables all work exactly the same. All right, and so once I choose the degree of confidence that I have, then I can go in and I look at the percentage of the population captured. So are we wanting 90% of all the data points, or 95 or 99? And you see that those three all repeat coming across here. Once I do that, I figure out what column I'm in of these two. So let's say we wanted a 95% confidence interval at 99% of all of the data captured, and then we would had 20 data points we were to read down, and that would be this value 3.615, and that would be my statistic. And that's all there is to it, to be able to capture all of the data. Now notice, what you notice is that the bandwidth, that the confidence interval width is growing in order to capture, because instead of trying to capture the mean, which will have a tendency toward the middle, we're now trying to capture all the data points, including the minimum and the maximum, with a certain degree of accuracy or of confidence for us to be able to do that. So that's what a tolerance interval is going to do for us. All right, it's a very easy process otherwise. Okay, so let's go through and we'll try an example. We started this example in the last video so that I could show the confidence interval for small samples. But to rehash, this is the ability of an individual to walk a straight line. And as I said in the last video, I'm not sure how they're quantifying this. I mean, personally, I can't walk a straight line anyway, so I would be one of the bad points in the data. But regardless, okay, the data given, N is 20, and then we've done some summations in order to help us calculate some things. Sum of xi is 18.51, the sample mean is 0.9255, sum of xi squared is 17.2555, okay, which allows us to calculate this Sx, which is the standard deviation numerator, okay, which is this term minus this guy squared divided by n, okay, and that number is 0.124495. So again, imagine you have a pile of numbers. I've done a lot of the data manipulation. I just want to show you kind of how the process works. Okay, once I have this SXX parameter, I can then calculate the sample variance, and that's SXX over n-1 gives me this number, 0.006552, and then if I take the square root of that, I get the sample standard deviation. So this is the one that we really need. I've got that guy now. So it's 0.080947 for that. Okay. Once we go in and we do that, in the last video we talked about finding our 95% confidence interval for a small sample. So I'll run through this again just because I want to be able to compare the values. And in case you haven't seen the previous video, this is where it's coming from. N is 20, that's less than 30, so we're going to do a small sample. Okay, a small sample tells me we're in the t distribution as opposed to the normal. Okay, we're going to go x bar plus or minus t alpha over 2 n-1. That's my statistic from the student t table. Okay, and then multiplied by s over the square root of n. So you've seen that one before. Okay, so we go through and we did our 100, 1 minus alpha is 95%, alpha is 5%, alpha over 2 is then 0.025%, and nu is n-1 or 19. And you can go into the student t tables for, again, now note that you're looking for the t statistic at alpha over 2. So this is a double-sided problem. Okay, so 0.025 goes in here, my n-1 is 19, that got me the statistic 2.093. And in the last video I showed you that in the table. Okay, by comparison, if this had been a normal distribution and a large sample, this statistic would have been 1.96. So you see it moved a little bit. It actually got a little bit wider. That t statistic is what sets the width on this thing. So we're about 5% higher on this. Maybe a little bit, actually maybe a little bit more than that, probably more like 6 or 7%. Okay, so the 95% confidence interval then, if I plug in my statistic of 2.093 back into this equation, multiply by s, divide by square root of n, add in x bar, the range is from 0.8876 to 0.09634. It would be my confidence interval for the population mean for a small sample. Okay, now getting into what we've done this time, we're now looking for, let's do a 95% prediction interval. So remember, the prediction interval is the interval that captures the next data point, or the next data, if I go in and I repeat the experiment, it's the next, the next parameter that we're going to read. So that's the prediction interval. So again, my S is 0.080947. We just calculated that. N is 20. Okay, so we can go in and do our values. Now again, what happens, you notice that the statistic itself is the same as what we just did up here. There's that 2.093 because it's T alpha over 2 and N minus 1. Again, we're looking at two-sided on this. The only thing that changes is this formula. The S is the same. It's that multiplier on the end of this thing, this square root of 1 plus 1 over N. All right, so if I plug in all my values, your 95% prediction interval is going to be 0.7519 and 1.0991. And again, as expected, the prediction interval, if you look, this guy is wider than the confidence interval. So if we kind of come in and look, my confidence interval was plotting here, my prediction interval is plotting here. Okay, in order to capture all the data. And it has to, because you don't know whether you're getting a low value or a high value or something in the middle to be able to do that. And so the prediction interval is always wider than the confidence interval of the same percentage. Okay, so, but it's very easy to calculate. Okay, the next one then is we want to find the interval that includes 99% of all values using a confidence interval of 95%. Okay, so this is a tolerance interval that we're going to look at. Okay, and so the formula we said was x bar plus or minus those critical values that came out of that table, okay, multiplied by the standard deviation of the sample. Okay, so in this, K is 99% because that's the percentage of all values that I'm after. The confidence interval is 95% because that's what the level of accuracy we wanted. And so from the table A6, and I showed you how to read these earlier, we're just going to pull off the value for these two parameters in an N of 20. The tolerance critical value is going to be 3.615. So my N is 20 on this thing. So that's all you need to get into that table. All right, so you can see that this is significantly larger than the statistics we were getting before. Before we had 2.093. Now we're looking to capture all of the data points, okay? And so we'll be good to go. And I think I misspoke earlier on the prediction interval. This was for the next data point, not for all of the data values. So disregard what I said on that. But the next data value, since I don't know whether I'm getting a high or low value, it is wider. That part is true, okay? Right. But for the tolerance interval, if I run the numbers using this formula and my statistic, you can see that the band is now 0.6329 and it's 1.2181 as the upper bound. So you can see that it's significantly larger now than the prediction interval, which was larger than the confidence interval. So if we go back to our graph, what's happening is now to capture all of the data, I've got to really expand this thing. So this is a PI, this is the PI, this is a TI, this is a TI, and this is a CI and a CI. And again, they were all 95% confidence intervals, but it spreads out quite a bit on that line, all right? Okay, so that's kind of the basics of it. We don't do a lot more than that in this class, but it can be pretty useful if you're trying to figure out, am I capturing all the data or if I'm just after the mean? It kind of depends on your application, what you're after. Okay, all right, but the thing to remember in all of these is that the prediction interval and the tolerance interval are both greater than the confidence interval of the same percentage. All right, so keep that in mind. All right. Another confidence interval that proves to be useful to us is the confidence interval for variance. All right, before we were always looking to locate the population mean or proportion or the next data point. Okay, but remember that variance is also a statistic. Okay, and it has its own probability distribution associated with it. All right, so to set this up, we're going to talk a little bit about its distribution. Okay, so for a random sample from a normal population with parameters mu and sigma squared, this is the relationship. N minus 1 over sigma squared times s squared is equal to the sum of xi minus x bar squared all over sigma squared. Okay, this equation has a chi-squared distribution. Okay, and so we use the Greek letter chi, and I'm not very good at writing it, but it kind of looks like a scripted x that's squished distribution with nu equal to n minus 1 degrees of freedom. So this part doesn't change. All right, and if I do it, we look at this table, it looks very different from a normal distribution, but it looks a lot like a t-distribution in the way that it's set up. So we have a chi-squared distribution, so we have different numerical values along here, and we have a chi-squared at some alpha value in nu, and we're looking for an area of alpha above above that point. Okay, so this would be our definition for a 1 minus alpha less than area that we're dealing with. Okay, now unlike the z and the t distributions, the chi-square distribution is not symmetric. Okay, it does not have zero mean. So what will happen is before we always had, in a normal distribution, if it was this, if I had plus 2.6 equals z here, at the end I always had minus 2.6. That was a symmetric distribution. Those two values matched, just the signs were different. That does not happen in this guy anymore. All right, so we got to be kind of careful when we're working with this. All right, so what we need to do is we need to have tabulated values for alpha near 0 and 1. Okay, so if I draw my chi-square distribution and I look at a double-sided on this, okay, if alpha is equal to 0.05, okay, then this is chi-squared at 97.5, and this is chi-squared at 2.5. These two areas don't necessarily, well, the areas may be the same, but there won't be a symmetrical number. I won't get a positive value here and a negative value here like we did with the standard normals. Okay. All right. Everything else is still fairly similar and fairly familiar to what we're doing on this. All right. So let's talk about the double-sided CI. Okay, the double-sided confidence interval. All right, so for a 100 times 1 minus alpha % confidence interval for sigma squared, that's the population variance, has a lower limit of n minus 1 times s squared, and then chi squared over alpha over 2 and n minus 1. So here's your statistic coming in here. Okay, and for an upper limit, we have n minus 1 times s squared times chi squared 1 minus alpha over 2 and n minus 1. Okay, that's how you handle a double-sided. For a single-sided, basically, if you want the lower limit on there, you're going to replace that lower statistic with chi squared alpha minus n minus 1. So notice we're dividing it by 2 here. I'm not here. So that's the shift. Exactly what we talked about with doubly sided in the previous video. So if you need to go back and take a look at those, please do so. All right, and then likewise for the upper limit, I'm taking this statistic and replacing it with the 1 minus alpha as the parameter. So that it's just you're changing that percentage that you're looking for. All right, so let's try it. It's fairly straightforward. Okay, so we've got an example. I've got a sample size of n equals 15. I've got sum of xi equal to 379.7. So my sum of xi squared is 9,646.37. My sxx parameter, we've done this a couple times now. Sum of xi squared minus sum of xi quantity squared over n gives me 34.89. So then my variance then is the sxx over n minus 1 gets me 2.49267. All right, so that gets me s squared, and that's the parameter that I'll need in my formulas for this because I need the variance. So to find a 95% confidence interval for the standard deviation, I'm going to do 100 times 1 minus alpha is 95. Alpha is 0.05. Alpha over 2 is 0.025. So that's exactly the same as what we've done before. Okay, now the chi-squared distribution comes out of the table A7. So just like we had different tables for tolerance, we've got a different one for chi-squared. So let's go find that real quick. I actually had it. That's going to be A7. Go to the right page here. Okay, and so it looks something kind of like that. And as you might expect, just like we did with the student t, it's just a different table. It's the chi-squared that works for variance. Okay, I look for my alpha value, and they've got some tabulated here for you. So if I want the alpha of 0.05 or the alpha over 2 of 0.025 is a common one. Okay, and all I do is I read down for the new value. So for us, we're looking at a sample size of 15. Okay, and I need, if I want the chi-squared of alpha over 2, I'm going to be looking at 27.488 would be the number I'm looking for. Okay, and hopefully that's the value that we pull off. Okay, and it's not. Make sure we get a parameter right, 15. And should be 14 because it's n equals 15, right? So n equals 15 tells me nu is 14. Okay, and then I go to my 0.025. There it is, 26.119. That's the number. Sorry, got my problems mixed up. But, all right, so clear as mud, right? Okay, hopefully that makes sense. All right, and so all we're doing is we're looking for the chi-squared of 0.025 and 14. Okay, gives me a number of 26.119. And then you do the same process, but now it's, remember, we're looking for 1 minus alpha over 2. That got me 0.975. So we go look for the chi-squared of 0.975, and 14 gets me 5.629. So you can see how they're not symmetrical anymore. Okay, and so then if I plug those values into my equations, I can pull off the confidence interval for the variance. Okay, so n minus 1 s squared over my lower statistic, and then n minus 1 s squared over my upper statistic. Okay, and again, be careful on this. It's written as chi-squared, but you're not actually squaring the term, okay, because it's already included in that. Okay, and so that gets me 1.3361 and 6.1996 as the confidence interval for the sigma squared. Okay, and then if I want the confidence interval for the standard deviation, all I do is I take the square root of those values. Okay, and that gets me 1.1559 and 2.48999 will be 95% confidence for the variance. Okay, if I want to find the upper limit for a one-sided distribution, then all I'm going to do is go take chi-squared of 0. And that should be the lower limit. Just realized. Yeah, be the lower limit. Chi-squared 0.05 and 14 gets me this statistic of 23.685. Will get me the location of that value. So my upper limit on the standard deviation then would be 1.21, and you can see that it pulls that line in a little bit relative to that value. So anyway, I hope that makes some sense. Like I said, I haven't done a lot with the variance of the confidence intervals, but at least you kind of know how they work now. And you know, when you take an advanced class in this, they'll do a lot more with the derivations and the math and the manipulation. I'm looking more at the skills as you try to set this forward. So anyway, I hope that made sense. And this video is a little bit shorter than some of the others, but we're kind of wrapping up the ends of our interval definitions so that we know how to find, you know, the next data point or the mean or any of the other statistics, or, you know, in this case, the variance also has its own distribution. And there's a lot of different distributions for a lot of different statistics, but by far the mean and the variance are probably two of the more important ones that we're going to look at. So anyway, I hope this all made sense. If you got any questions, give me a holler, leave a comment down below. That would be great. And as always, like the video if you would, and be sure to subscribe to the channel. And with that, we'll bid you an awesome good morning. So good morning. Happy engineering.